So this is a summary video for 9.2. It's going to be a little bit quicker. I'm not going to dwell on too many things, but for 9.2 we're talking about analyzing rational functions, and one of the big things that we want to analyze is why a rational function sometimes looks like a straight line. We touched on this a little bit in 9.1, but I'm going to answer this question: why is this graph a straight line when its equation looks quite complex? And as you see here, it's a bit exaggerated, but there's a hole. Okay, if I zoom in there is a gap right here in this. Now that gap represents the x value that is restricted in this equation. You see that? So x equals 1, 2, 3 is where this gap is. Now notice that when we have a restricted value, that's when we have either a gap discontinuity like this, or what else? A restricted value, let's say an x value that's restricted because it makes the denominator 0. What's the other option? It could be a what? An asymptote, a vertical asymptote, okay? So why is there no vertical asymptote here? It's just a gap. It's because if we factor the top here, factor the numerator, that's going to be, we're going to factor in, it's a quadratic. So if we factor that, we need two numbers that multiply to positive 6, add up to negative 5. So it looks like this, right? Negative 2, negative 3. Because we have the situation when simplified that these two factors divide out, okay? If that's the case, if this can be simplified, look at what it simplifies to. Y equals x minus 2. That's what it simplifies to. And so guess what? That's actually what this graph is going to look like, with the exception that at x equals positive 3, that refers to this restricted value here, there's going to be a gap. Okay? So the bottom line is here, if you want to find out what this graph looks like, factor the top and the bottom and divide out any common factors. Once you do that, you get to see what the graph will end up looking like. Now it is important to note that before you divide all this out and get rid of it all, you have to take note of what the restrictions are in the equation. And that will either represent a vertical asymptote or a gap discontinuity. If in the simplified form, so let's say another example here, in simplified form we actually have this, x plus 2 over x minus 3, and let's say that's what was left over, and this wasn't able to be divided out, then we do have a vertical asymptote at x equals positive 3 here. All right, and let's graph this just to see. Okay, so go ahead on your graphing calculator, take a moment to graph that, and we'll just see. Okay, so on your graphing calculator, I adjusted my window a bit, but this is what it should look like. The TI-83 shows you actually a black line that would be the vertical asymptote, and it goes through 1, 2, 3, right there, positive 3. In Desmos here, the 3 would be right about here, I guess, and so that's your vertical asymptote. You could zoom in and see that right there. Anyways, so that's what it looks like. Now, if that's because in the simplified form, this remains in the denominator. If it remains in the denominator, then you have a vertical asymptote here. Okay, so what happens if you have, let's just say we have more than one binomial, or more than one sort of binomial factor in the denominator. So what happens? Ooh, look at that. Look at how that changed. So what about this? X minus 1. If we put that in there, look at how this changes. So we actually have a vertical asymptote at x equals 1. Right there. And we also have a vertical asymptote at x equals 3. All right, so there's lots of things happening here. Now, what does this graph look like? If you don't know, if you don't have this, if you just have this, what does this graph look like? Well, you can find out a couple things. You can find out where your vertical asymptotes are, no problem. You can also find out where your y-intercept is pretty easily by letting x equal 0. And in that case, if you let x equal 0, that's going to be 2 divided by negative 3 times negative 1. That's 2 over 3. Right? So we look here. There we go, 0.667. You see that? So you can have your asymptotes. You can have your y-intercept. We also can look at the degree of the numerator. and that's degree 1. What's the degree of the denominator here? 2. That's a quadratic. So when we have the degree in the numerator is less, where's our horizontal asymptote? Always at 0. Remember we talked a little bit about that last lesson? Yes, no? When the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is always 0. And how you can test that is pick a number, like a large number, like 100. So what happens when you have 100 here? Well, that's 102 divided by, basically 97 times 99. So that's 100. That's a smaller number divided by a much larger number. So it's going to be closer and closer and closer to 0. You pick a billion. So this is a billion and 2, basically divided by a billion squared, right? So that's, close to 0. So that's just the way it works out. All right. So we have either a gap or a vertical asymptote. If there are no restricted values or no non-permissible values, then we have neither. Okay, we have neither a gap nor a vertical asymptote. So I'm just going to actually just point you here. So this is what we talked about. The graph of a rational function either has a vertical asymptote, that's when a factor remains in the denominator after simplification, or a point of discontinuity. This is a restricted value that eventually would get divided out of the simplified equation. Okay, that's a point of discontinuity. And they would always correspond to the non-permissible values that you see there. If there are no non-permissible values, then it has no asymptotes or points of discontinuity. It would be just a straight line, or whatever, a parabola or whatever with no discontinuity. So to find any x-intercepts, points of discontinuity, and vertical asymptotes of the rational function, we analyze the numerator and the denominator. So this is what we'll focus on here next. A factor of only the numerator corresponds to an x-intercept. So if we go back to our notes here, a factor of only the numerator. So notice this. This is a factor of only the numerator. So how does this correspond to an x-intercept? I don't have that one graphed anymore, do I? Well, I tell you what. What about this one right here? Look at this original graph here. Ooh, yikes. Okay, let me circle this for you. This right here. This is a factor of only the numerator. How does that correspond to this graph? Check out the x-intercept there. See that? It's what makes this 0. So x equals 2 is our x-intercept. So that's what that point means. If the factor is only in the numerator, then it's an x-intercept. A factor only in the denominator, so that means it's still there after simplification, that's your vertical asymptote. A factor of both, and of course that's what we talk about when we divide it out. Here's a factor of both. What does that refer to? That refers to a point of discontinuity or a gap in the graph. Make sense? Okay, to analyze the behavior of a function near a non-permissible value, use a table of values or a graph even though the function is undefined or does not exist. Now, this point right here, I'll just spend a minute on this point here. But if you want to know what's happening near that gap or near that asymptote, then you can just do a quick test of some point that's really close. Like, for example, if we go back here, if we didn't have this graph, okay, and I knew that 3 was a non-permissible value, and I wanted to know what the graph looked like near 3, I would simply just do, let's put an x value that's near 3, like 3.01, right, minus 2. And you calculate that, and what's that, 1.01? So 1.01, that's the y value of the graph that's very near x equals 3. So does that make sense? If it's just beyond 3, it's 1.01. It's right there. This becomes really handy when we're dealing with something like this. I know that x equals 3 is a vertical asymptote. So what if I put 3.01? I would see kind of where that graph is near 3. So 3.01 plus 2 over 3.01 minus 3. That is 5.01, and this is 0.01. So what is this? That is 501. So guess what? Just beyond 3, this non-permissible value, the value of the function is huge. And that should correspond to 1, 2, 3. Here's our vertical asymptote, and so the y value is super large, like way up here. And that would make sense if the graph looks something like this, right? So that's how you can test kind of what that graph looks like near one of those points. Okay, that's a lot of information. Like I say, it's going pretty quick. But do you have any questions so far? All right, so I went over all these key ideas. Now there will be examples that we'll do here, but that's sort of your summary lesson for 9.2, which, like I say, I've already kind of covered a little bit of that before today. So yeah, here are the ideas, key ideas, and we did some examples there. Whoa, that's moving pretty fast. So that's the wrap up for that lesson. So in this first question in your assignment, I'm going to do this first question with you here. What are the non-permissible values? How do we find the non-permissible values? Yes, factor everything. Factor the top, factor the bottom. The top is already factored, so if we have x minus 4 up top there, how do we factor the bottom? Well, that's a quadratic. We'd probably be able to factor that by sight. 2 numbers that multiply to positive 8 and add to negative 6. Do you have anything like that? Okay, so x minus 4 and x minus 2. Good with that? All right, so non-permissible values. They are x cannot equal positive 4 and positive 2. However you write that, that's fine. Non-permissible values are 4 and 2. So this question says the feature that is exhibited at each non-permissible value. So is it an asymptote? Is it a gap? What's happening? Well, at 2, what's happening at x equals 2? Asymptote, right, because it is not going to get divided out. It's going to be left there. So here's the simplified version, right? Look at x minus 4, that's gone. What's left over is going to be 1 over x minus 2. That's what the graph is going to look like. That's what it's going to look like. And so at positive 2, okay, vertical asymptote. And at positive 4, what's happening there? It's a gap because this factor gets divided out, so that's a gap. Now we do have the benefit of seeing this right up here. Look at 2, there's your asymptote, and 4, here's your gap. See that? So each restricted value, non-permissible value, corresponds to one of those. So behavior near the non-permissible value, okay, so with this one, you might want to test out values like I said. If you can see the graph, you can see that what is x, if you put x equals 4 in here into the simplified version, you're going to get, and again, this is a calculus thing, so we're getting into kind of calculus ideas here. If you simply plug 4 in there, that is the value that this graph is going to approach. That is the limit of that function, coming close, really, really close to this x value of 4. So in the simplified version, if you plug 4 in, you get what? 1/2. Guess what? Y equals 1/2 is the y value that this graph approaches. I'm just going to zoom in there. So look at this. In the simplified version, if you put 4 in, you're not going to get a restricted, situation. And you're going to see here's 1/2. This is what this graph actually approaches. So that's a little helpful hint here, hopefully for you. And then, of course, the graph here, as we can see to the right of x equals 2, the graph approaches infinity. So when you see a graph going up like this towards a vertical asymptote, that is approaching infinity. Those are the words that we use there. And again, this is prepping you for calculus, right? Approaching infinity, that's terminology you need to know. On the left side of 2, the graph approaches what? Negative infinity. Thank you very much. Negative infinity. For domain, I'm not really sure what the book is requiring of you. The domain is all values of x except for x equals 2 and x equals 4. So I'm not, like I say, I'm not really sure how you're allowed right now. For me, if you say x cannot equal 2 or 4, I'm sort of okay with that. How we would express that as all the possible values of x would be this. Domain equals, x would be okay from negative infinity to 2, right? So, from negative infinity, as well as, and this is why I'm not going to need you to do this right now, as well as from 2 to 4, as well as x greater than 4. So you see how this is expressing the pieces of the actual domain. That's what x can be. This is what x can be. This is what x can be. Right now, if you say domain is, you cannot have 2 and 4, I'm okay with that right now. Because I just want you to learn about rational functions. But that's kind of how you would write. Okay. So yeah, the question was asked, can you just write this, x is less than 2? That's totally fine too, actually. I kind of want to get that infinity in there, but yes, I guess I did it over here. So yeah, you could write like this as well. Yeah, good call.